Welcome everyone, and thanks Chirag for having me. One thing before we dive into AI interpretability, because you are stuck with me on the screen for the next hour. So to make up for this, I want this to feel like a conversation between I and you, not me talking at the word all the time, or at the word all the time. So here's the plan. We will have 4 parts, and after each part, I will stop for a few questions. If you have you just raise your questions. So today's topic is AI interpretability. The narrative is we are moving from tools that explain an AI after we build it to the AI that is transparent by design. So, okay, let's dive into the AI interpretability. So a quick housekeeping before we start. Interpretability is really a tongue twister for me. So sometimes I will just say interp for short, and mechanistic interpretability, I will shorten to make interp. So okay, let's just dive in. So let's rewind a little bit. We are going back to the dinosaur days of interpretability, and I promise it's kind of fun. So the first question, what is AI interpretability, right? AI interpretability means explaining how an AI model makes a decision so a person can understand it and trust it. But why do we even care about the model interpretability or model explanation? For the 3 reasons I argue, the first one is we want to trust AI models. We want to catch their mistakes. And finally, we want to make the model we are using to be safe. The question I want you to hold for the whole talk is, when an AI gives us an answer, can we tell why? Okay. So let's make this a little bit more concrete, because you're probably using AI every day. For example, when Spotify or YouTube Music recommends a song, or your phone auto-completes a word, do you care why it did that? Usually it's not. If it's wrong, you just skip the song or the completion. But now picture an AI that reads your essay and flags it for the plagiarism, or a system that decides a loan or a medical chatbot telling you what is wrong with your body, right? In those cases, just a model answer is not enough. And you want to know why it decided that? Here's the thing. The more we ask AI for decisions, the more we need to see its reasoning. So this fun interpretability is not new. It has been around far longer than today AI chatbots like ChatGPT or Cloud. It got popular with images. For example, you can highlight which parts of a photo made an AI say cat back then, like I think like more than almost 15 years ago. Then AI chatbots arrived, ChatGPT, Cloud, Gemini, and they brought many new problems. They sometimes make things up, and they say it with the total confidence. So if you look at this example, someone asked a medical question: can I take ibuprofen with my blood pressure pills? And if you look at the reasoning here, the model is basically thinking, this seems routine, so I will just give the yes answer, right? And its answer like, hey, take it, it's completely safe. That answer is wrong. And in medicine, a confident wrong answer can be dangerous or fatal. So the circle part here is the model explaining its own thinking, or people call it chain of thought these days, which is one simple kind of self-explanation, the model explaining itself. So there's another way to explain the AI after we build it, and we explain them by like external tools. Researchers call that post-hoc methods, and that's where we are heading next for the next part of the talk. Okay, so I just give you the background and the very history of the interpretability, why we need AI. Okay, sounds good. So we got the background of AI interpretability. And in this part, because we know that AI can self-explain itself, and there's another way to explain AI models It is we are using external tools to explain the model we are trying to explain. And this is an ambitious one. So in the community right now, we have something called mechanistic interpretability. And so basically what we are doing is we open up a chain model and look at the parts inside. So let me dive into it. Okay, so a little bit of the background. There are actually many ways to explain an AI models. We already met one, the AI experience itself, which can be unreliable, as I told you. The second big family is post-hoc interpretability, the middle one here, where we explain the AI after we build it. And the third one, which we will get into later, is by design interpretability, where we build the AI to be interpretable from the start. And there are many other, for now, we are just zooming into the post-hoc method for like a mechanistic interpretability here. Okay, so let's look at a popular and powerful tool for mechanistic interpretability, the sparse autoencoder or SAE. Here's the problem it solves. A single neuron usually fires for many unrelated things at once. For example, just one neuron in our normal network will activate for the cats, for the color red, and for Python code patterns. We call that polysemanticity, meaning a neuron containing many semantics or many meanings. So an SAE here, it rewrites that dense activity or dense activation of the original model into a sparse set of features. And the goal is that one feature lines up with one human understandable concept so that every model prediction can be explained by a set of human concepts. Okay, so here's an autoencoder or SAE. On the left is an activation from the model you want to explain, X. It is dense, meaning every number is doing multiple jobs at once. The encoder, this encoder, it maps X into F, a much wider and sparse vector that is almost zero, where each active entry here, you can see the blue one, this stands for one concept. Then the decoder take the F here and try to rebuild or try to reconstruct the original activation. And we got the X head. And so a popular question is why we are reconstructing the activation. The reason is because if you can rebuild X here, the original one activation, from just a few active concepts, those concepts must capture what the original activation was really doing. We then read the sparse activation or the sparse feature F here as the explanation for the original dense activation or the black box model here. Okay, so here is how we chain an SAE. To chain the SAE on, we chain the SAE on lots of activations from the model we are trying to explain. The loss function have two parts. The first is a reconstruction activation. So the X head here should match the original X, activation X. Second, the sparsity penalty, the lambda times the L1 norm of F, which forces most features to be zero. So only a few activate at once. We want sparsity here for human understanding and easy control over the output. Then at the test time, we feed a new activation from the original model, run just the encoder to get the sparse feature F and read which features turned on. This works pretty well on the real models like Cloud. Here's a fun example from Anthropic. So they found a feature inside Cloud that activates for the Golden Gate Bridge in San Francisco. Then what they did is they turned that feature up. Now, if we watch, someone asked a totally ordinary question, what should I do with $10? And the model now cannot stop talking about the bridge. It tells you to go pay the toll and enjoy the orange towers. So I think it's pretty funny. But the point here is kind of serious. Like finding a feature means we can also steer it and control the model output. That is, we tune it up or down to push or control the model behavior. The interesting model steering, we will come back in the next part of the talk. The anthropic researchers, they also found the safety relevant features, like ones for unsafe code generation, the deception of users, and the bias. I think that is a strong use case for this whole approach, mechanistic interpretability. So I want to give it the real credit here before which I show that it's actually struggle. Okay, so good. So far, mechanistic interpretability is working so well. It can find you like a super interesting features like bias, a deception, or like a golden gate bridge. But the first problem of the mechanistic interpretability or the SAE is we need to train one sparse autoencoder, and actually like a training one sparse autoencoder is cheap next to training like the whole like a cloud or ChatGPT model itself. The real cost is that it's a whole second pipeline. You run the full original model, right, on the huge amount of data to collect activations to train the SAE, and you store all of that. Then you train a separate autoencoder for each layer and each place you want to look. And in cloud ChatGPT or like any big models, we have many and many layers, and there's countless of places you can like probe to like train an SAE. And the dictionaries here or like a storage here have to be huge into millions to billions of features, and they grow much faster with the model size. So every time with the base model changes, you redo it, you retrain the SAE. On top of that, I think like a fully reverse engineering a large model, a large language model, it's just so impractical. It's not doable. So to confirm that, the researchers at Google DeepMind, they also argue that we should pivot to what they call pragmatic interpretability. They steer from like a mechanistic interpretability, trying to reverse engineer the whole model, to pragmatic interpretability, meaning they just try to solve the concrete safety problems instead of chasing a complete map of the model. And the second problem is deeper, and I think it's more serious, and it inspires the rest of the talk. We need to set up two things here. First, an explanation is plausible if it looks convincing to a person, and it is an explanation is faithful if it actually matches what the model did inside. But the scary part here is they can come apart. A method can give you a clean, convincing story that has nothing to do with the real model reasoning. So last year, researchers ran sparse autoencoders on a random untrained network, one that computes nothing meaningful, and still got nice, interpretable looking features out of the SAE. So it's kind of bizarre. It was a pretty shocking result to me last year. So I think that, is a recent paper, it's called like a dead salmon problem in AI interpretability. They echo a famous neuroscience example. So a team put a dead salmon into the brain scanner, and they scanned the activity. So the fish was very much dead, but ridiculously, the scanners were just picking up the noise, and the analysis dressed up as a signal. And people call this a dead salmon problem. So I think the takeaway here is post-hoc tools like mechanistic interpretability or SAE can give you plausible without faithful. They can, or like sometimes they can be faithful, but they can give you like something plausible without faithful. We will dive into faithfulness later. Okay, so that's it for the interp or like a mechanistic interpretability. Okay, so sounds great. So now let's get into the next part of interpretability, and this one I'm advocating for it. So maybe I'm a little bit biased. So please pardon me in advance. So, okay, now let's get to the by design interpretability. So if post-hoc explanations can be unfaithful, here's a question I want to ask. Can we just build a model that is interpretable by design? There's no second model to explain the first, and the concepts live inside the model itself natively. We don't need the concept discovery. We just like append the model with the concepts. We can train the model with the concepts being specified beforehand. Can we do that? So here's I put like two approaches side by side, the post-hoc and the by design interp. So you can see the real advantage here of by design interpretability. We don't need the second model. And the faithfulness, when the post-hoc or SAEs, they're still facing the faithfulness crisis. The by design model, you always have the faithful explanations. And for steering empirically, we are showing that we can control hundreds of thousands of concepts. While if you just use SAEs or like a post-hoc methods, I believe you can just not just I believe, it's in the literature, it's showing that you can control several to just dozens of concepts. And the cost here, I don't think there's huge advantage of interpretable by design here. But the cost is, in the post-hoc, we pay the cost after training because we build the model and we explain it. But by design, we pay during training. It means we put an interpretability into the training process. I will get into details later. But this is the difference between a post-hoc interpretability and by design interpretability. Okay, so by design interpretability, let's take an example. This is stealing HB from Guy Labs, where I'm working at. This is the first interpretable by design language model at this scale. It's 8 billion parameters network. And here's the whole idea in one picture. So we have a prompt as the older candidate and the younger candidate applied. The better higher is. So the prompt goes in on the left, in the middle. Every prediction or every model output has to pass through a layer of human understandable concepts. And we have 100,000 of them. For this prompt, the concepts like job suitability and hiring context lies up. And the answer on the right here is a better hire. The answer here is the younger candidate. And the answer is computed straight from whichever concepts are active. You can just read which concepts activated and understand why the model chose what it chose. The explanation is not a separate analysis as we are doing with a post methods. It's a real computation of the model. Okay, so I'm showing this the same way as the SAE slide on purpose, so you can compare. So the difference is that the bottleneck isn't added on afterward. It's a part of the forward pass for our hiring question, the hiring question we had before. So hidden state from the backbone gets projected onto the name concepts, like job suitability is activating, hiring concepts is activating, the finance it doesn't, and sparse it doesn't. A sparse, few of them light up here, and the answer is computed exactly from those concepts. So the explanation is just like you read out from whatever the computation giving you. Okay, so I think we go back to your question about the age. Actually, when we pass the same question, there's another concept lighting up, is the age bias. We give the interpretable by design model a prompt, and actually it's at risk of the bias completion or like a bias answer, right? So the hiring question that mentioned the older and younger candidate, and it say that the young candidate. So we look at the what concepts are activating, and they are pretty suitable, the job suitability, the hiring context. But one of them, like a highly activating, is an age bias concept. And it lights up strongly, and you can see it directly here. And I think we can somehow conclude that the model is a little bit biased here. Okay, so here's the highlight. We take that age bias concepts and we suppress it at the inference time, and we rerun. The concept drops, I think, the activation from 0.83 down to near zero here. So completion changes to something about matching experience to the role. And this is the important part. We never touch the ways like the fine-tuning paradigm. It's a closed loop steering. We diagnose a concept, we steer it directly, and there's no retraining or no fine-tuning. So if you compare that to like a fine-tuning, which will edit the weights globally and can quietly hurt other capabilities. Okay, so now I think this is a fair question. So if you force the model to be interpretable, do you sacrifice its performance, like coding or math? So here's our empirical evidence. H dot is a model. Up is a benchmark on the math and coding, etc. And the right is more training compute, more data on the log scale. So steering is a purple dot here. It sits at the far left because it uses the least compute of any model here. And look at great lengths. It beats like a comparable size models like a Llama 2 and DeepSeek 7B. And it stays in the same neighborhood as a model that uses 2 to 16 times more compute or data. So interpretable, you can see here, they are much more expensive to train, but we are in the like a same neighborhood. So interpretable by design model with the least data and the least computation still perform pretty competitively with other models. And here is a more interesting result, and it's actually a pretty surprising for us as well, because we found the interpretability does not get worse as the model gets bigger. Because in AIs, I think people always have an argument that the more you scale, the bigger the model, the more black box it is. But in our case, when we try to get the model interpretable by design, the interpretability just get better. And there's a reference here if you're interested in the metric here, or like how is it better, how much is it? And the concepts became more independent and more meaningful in the larger models. So the model gets easier to understand, it gets more capable. So we scale from 800 million parameters to 8 billion parameters, and we see this like keep increasing. So it's a super interesting result for us. So imagine if you scale it to like a ChatGPT or like a cloud size, and you get like a very capable model, and the model can still give you like a faithful explanation. So it should be great, right? Okay, so let me state the big picture here, because this is the conclusion for this part, interpretable by design. We usually treat interpretable as a cost we pay against capability. We tested whether that cost grows as the models get bigger, and it does not. It does not. The real change is where the interpretable enters. So in this model, in the standard recipe, when you train a normal model, right, you just train it with to maximize the performance, and then you go back, you use the post-hoc tools to discover the things, or like to try to explain the model very locally. And it doesn't, often it doesn't guarantee the faithful explanation. So we flip that entirely, we flip that paradigm entirely. We ask what conditions make an explanation faithful in the first place, and we build those conditions into the data training and the data curation, the model architecture, the objective, and the losses. And because the same concept variables drive both explanation and the control, so you can take an output, you see the concepts behind it, edit the one you care about without training. So in short, if interpretability can be specified, can be trained, and scale like any other capability, then the opacity of today's most capable models can be solved. So we finished 3 parts. And we go to the future of AI interpretability. Okay, so we said we need faithful explanations of how an AI reasons. And we just show that you can actually have them without giving up the performance, even at scale. So the question for the future is just how far can we push it? Let me give you like two directions or my takes. So direction one, the first idea is to build or to put the interpretability design all the way into training. With the steering model from GuideLabs, we did not just add a concept layer at the end. We carry the faithfulness and interpretability constraints through the entire pipeline, from data annotation to pre-training, then through mid-training, and all the way to post-training. And that is the point. When the constraints hold at every stage, you do not have to wonder whether the explanation is reliable or not. Whatever the explanation says, you can trust it. And the future direction is to push this further. For example, if you train the model to the RLHF or DPO, so we should put the interpretability or like faithfulness constraints into the reward objectives or like agent training, or like put into like the proactive agent pipeline right now. And another direction is automated interpretability. So I think it's somehow related to the question about the verbalizer Chirag asked before. So right now, a human reads these explanations, but I think it's so impossible because there's so many to read by hand. The information is too dense. I think like I get headache sometimes just like looking at the model thinking and to try to justify the model answer. So we can let an AI read them instead. I give an example here in the loop. So a model makes a decision and its concept light up. An AI model, like you can use ChatGPT, Cloud, or like a Giang model itself, this model itself, reads those concepts, spot a problem here. For example, the bias concept on our hiring question, steer it down and fix it. So humans is not in the loop. So I think that's something people call self-recursive AI. I mean, like it has so many variants, but here I just like try to initiate a instance with interpretability. And pretty much I believe in the self-recursion via like interpretability. And the same idea here can also help people. When the computation is too dense for a person to read, and an AI can digest it and hand you a short and faithful model reasoning insights. And actually in GuideLabs, we are building this kind of idea. So by design is very important here because the AI is reading concepts the model already exposed. So the reading is reading something faithful, and you can choose the verbalizer as well, and you can put some constraints to verbalizer to make it even like a faithful and make it useful for the downstream task. Okay, so here come to the last slide of my talk. Let me bring everything together with a quick recap. In part one, we learned about AI interpretability. In part two, mechanistic methods like sparse autoencoder or SAE open up the whole model. But we saw that post-hoc explanations can look plausible without being faithful. And in the part three, by design brings the faithfulness in. So the explanation is a computation itself, and it scales all the way from 100 million parameters to 8 billion parameters of LLMs. So the shift is going from explaining an AI after the fact to designing one that can understand from the start, from the beginning. So that's the whole talk. You may ask where you can actually try the Interpretable-by-Design LLM. We built the steering. So we open source everything for the model on GitHub with the link here. And this is my website for more information, or like if you have any follow-up question, inquiries, please take it away. And now I'm happy to take your questions. Thank you very much for listening.